kind of have a fun class in that we will be trying out some group work. So it's going to be a little bit different. It's going to be online group work. And essentially what we're going to do is we're just going to continue from where we left off last class. And essentially our goal is to classify different voxels within our mass. So if you think to what the ultimate goal of this course is to generate these buildings that sort of teach practical skills like how do you meet FSR requirements, how do you meet site coverage requirements, how do you consider, solar envelopes, things like that. Also to build up a sort of solid foundation in Grasshopper, but it's also to sort of have fun and build these cool agglomerations of modular pieces. So for example, the file that I have open is the site file. So if you want to follow along with me and you don't have your file open under the syllabus assignments, island model and lots link, there is again the assignment site Rhino 5. And this hasn't changed since last class. And so feel free to open it. And in here, what you'll see is we have these pieces down in the corner here by the notes, where we need to figure out how to essentially take these pieces. So for example, a piece which is exposed on 3 of its 4 sides, its top and its bottom, and how can we sort of take that and apply it to all the pieces like this one right there, that sort of meet the requirements that that piece needs. So how do we classify the different chunks in this tower? So if you open this file, you can see that there's a few different classifications that I've sort of, thought of. So as I mentioned last class, I sort of am basing this on an algorithm called marching cubes. But in this case, the sorts of units we can have in our massive voxels are interiors, which are spaces like these, column pieces, which are spaces like these. So for instance, the column roof right here is something that happens in your voxel pile when you have a condition like, let's say, this one right here. You see, it's exposed on 4 sides, not on the bottom, but on the top. So that's a column roof. We have what I'm calling tunnels. So these tunnels are essentially pieces which are exposed on 2 sides, but connect to interior spaces on the inside. So within those tunnels, we have a tunnel roof, a tunnel that's, interior space on both the top and the bottom, the tunnel bottom, which means that its bottom size is exposed, and also the tunnel floater, which means both its top and its bottom are exposed. We have corner pieces. So everywhere there's a corner in our pile of voxels. So for example, right here, I'm looking at the mouse offset, for example, right here, we can consider this a corner piece. So in the case of this corner I'm pointing to, and I'm aware of the arrow offset, so this is the right square you're seeing, this voxel here I would consider a top corner because it has one side exposed, another side exposed, as well as the top exposed. This corner right here, for instance, would just be a standard corner piece. Standard corner relating to the corner layer right there. And this piece down at the bottom would be a corner bottom piece, for instance. So that's how we're kind of thinking about these kind of things. I guess just to go over the last few types. So there's side faces. Those are faces or voxels where all sides are covered except for one. So for example, all of these faces across the row here are side faces, but these faces here are side faces with the top exposed. Finally, the last kind that I kind of found was what I was calling nubs. And these nubs are any pieces that stick out and they're exposed on 3 sides, and then, a combination of top, bottom, or top and bottom like this. So for example, I'd consider this a nubs floater. So these kind of this kind of language like floaters and nubs and whatnot, I just came up with. You can use your own kind of classification system if you wish, but it might be easier for everyone to just call their pieces by these labels I've come up with. So that's what we're going to spend this class doing, is we're going to figure out how to take this pile of voxels and classify them. To do that, we're going to continue with the grasshopper file we ended with last class. So you can find this in two places. If you already have it open, we'll be working with the voxels part 2 from last class. So that's the 2007-08 voxels part 3. So that's the kind of grasshopper definition we ended on last class. Or if you want, I've just copied that over to today's date. So 2007-13 and then 2007-13 voxel classification. So you can open that file and we'll all start from that place. I'm going to take you through kind of one example because I can understand if what we're doing here is maybe not the most clear right now. So I'm going to take you through one or two examples of what we'll do. And then what we're going to do afterwards is we're going to break out into groups, and you are going to try to classify some of these voxels by yourself in a group. So if you go to the Dropbox and in the syllabus assignments, island model and lots link, there is an islands lot link, of course, which will lead you to this spreadsheet, which should look familiar to all of you. But what I have done now is below this map and where you had written all your names, where you sort of claimed your site, you'll see there's a new map which I've so artfully overlaid a sort of a bunch of neighborhoods. And these will define our groups for the rest of the class. So I've tried to keep it around 5 or 6 or 7 people, kind of 5 to 7 people per group. And essentially, these are going to be the groups that you guys will be sort of working in. When the time comes to work in groups, what we're going to do is we're going to in Collaborate Ultra, so there we are, our infinite regression. We are going to try to go to breakout groups, and I will essentially try to break up these groups with your names corresponding to these groups here. So I've never done this live. I practiced last night non-live, so hopefully I can figure out, but that's sort of the goal for this. So does anyone have any questions before we sort of jump into the example? Erica, are we able to work with our own site? Yeah, so just to confirm, when I'm talking about the groups here, these groups, we're not doing a group project, as it were. Your final assignment will be your own final assignment. But what you will find is that just the amount of work that it might take some of you guys who maybe aren't as familiar with Grasshopper to figure out all of the combinations for all these voxels will be a huge amount of work. So to make the amount of work kind of more feasible for a 3-credit course, the group work really will come in handy. It's the kind of thing where there's like, how many classifications are there here? There's, 3 times, so there's 8, 16, 20, 23. So there's 23 classifications of voxels. To figure these out by yourself, it took me the better part of an afternoon. For someone who's newer in Grasshopper, it might take a couple days. I don't intend to assign you guys like 16 hours of homework, so that's why we're breaking this work up into groups. But you will still be responsible for taking that and making your own design. And in the end, everyone's sites will be very unique. So it's just a way to reduce work. If you do want to tackle, creating all of these voxel classifications by yourself, feel free to do so, but I would encourage you to, participate with your group at least during class time, and then just let your group know, hey, I'll contribute one, but I'm going to recreate them all by myself. Okay, so I am going to get started on where we left off last class. So I have the site model open. I'm going to open Grasshopper, and I am going to open the Grasshopper file in today's class. So I'm also going to open my own notes, just so I don't get far off course. This will also give you a preview of the amount of grasshoppering that we're going to do, and the reason why I suggest that we do this in groups, because as you can see, this is a lot of stuff. Most of it's kind of repeated, but definitely breaking this up between a few different people will help us out a lot. So what I'm going to do is I'm just going to copy this stuff here just to make sure I can refer to it. Okay, great. All right. So when you open this Grasshopper file, or maybe it's your own Grasshopper file that you're working from, essentially there's going to be a few things here. There's going to be your voxel input, which for me it looks like it's not referencing correctly, so I'm going to re-reference. That's fine. So essentially what this voxel input is it is all of our voxels in the file. So what I'm going to do is, if you do need to re-reference it, these voxels are going to be on the TGE FSR voxels 9.5 FSR layer. So I can just right-click this layer, go select objects, selecting all the meshes on that layer. So you can see 972 meshes selected. This might be your own. This might be your own pile of voxels, and once you have them selected, you can just right-click on the voxel input and go set multiple meshes. Okay. Now, what the other things we have in this definition is we have these bounding box points. Now, we'll reset them just in case you need to review these, or you want to set them on your own pile of voxels. So to do this, all these are is, if we zoom down, they're essentially 3 points, so an X, a Y, or a origin, an X, and a Y point. Maybe I'll switch to wireframe so it's easier to see. So yeah, so you can see an origin point, a point that defines an X-axis, and a point that defines a Y-axis. And essentially these just form the plane on which these bounding boxes are made. So we want them to more or less exactly align with our voxels. So to set them, what we can do is we can right click and go set multiple points, and you want to make sure that type equals coordinate is popping up in your command line. If it's not, you can just click the type equals, set it to coordinate. Make sure that you have vertex snapping on, and make sure that project is off. So vertex snap on. And once vertex snap is on, then you can just click at the corners of your voxels. So you just want to select one of your voxels. I'm just selecting the one that seems, on the lower right-hand corner, just because it's the closest one to my viewport. And I'm going to select the origin first, then the X point, and then the Y point, and then hit enter. So origin, X, Y, enter. And that will take those 3 points to create a plane 3-point using the component plane 3-point. And then from there, you can see we have a bounding box, and we've set the bounding box component to create a bounding box per object. So it's not creating one bounding box around all of these, it's one bounding box per voxel. The other thing we did after this is, if you remember from last class, we looked at the corners of all these boxes, and using a little bit of simple averaging of corner points, we found the center points of all the faces of the boxes. So for example, let's look at the south face. So the south face is essentially the face that is the, we can consider it the local south of our site. So if we look at our, the map of Anabab, we essentially, south is straight down, right? Like there's our universal, our world north arrow. Now, we're sort of considering this as a local south because our bounding boxes are aligned to our site and not to the world's north, south, east, west. So what we're considering south is this edge right there. And I'm selecting the right place in your screen. So the arrow offset is taken into consideration. So this is south, this is north, east, south, west. And we're doing that because the local plane that we set right here. So here, why don't I hide these so I can see it? Because this local plane that we set here, you can see that that's its y-axis and this is its x-axis. So essentially this is our local north, positive y, east, positive x, south, negative y, west, negative x. So that's what we mean when we say north, south, east, west in this context. And for your own, actually let's switch to wireframe again. For your own project, you'll probably choose a similar style of local north, south, east, west. So whatever makes sense for you. So that's what we're doing there. And like I said, from averaging the corners of those points, we're getting, for example, all the south points. So you can see all these points are on the local south of these voxels. For example, all of the top faces. So we have all the top faces there. You can see they're on top. And bottom faces, etc., etc. So refer to last class's YouTube video if you need a quick refresher of how we did that. Now, the way we tested, so the way that we're kind of saying we're classifying these voxels is whether or not a face is exposed, right? So for example, we have this piece here, which we're considering a column roof, and the reason why we're calling it a column roof is if we look at the shapes over here. So these layers in the file are, I should mention, are organized from left to right. So for example, if we want a column roof, I can just select objects as this one here. You can see a column roof is just something that's exposed on all four sides as well as in the top, right? So this is the one we looked at before. It's kind of, it looks like almost like a little lookout tower or something. So it's exposed on all four sides and then it's a roof. So that's why we're saying that this piece here is a column top, right? And we know it's a column top because we can say the north side is exposed, the east side is exposed, the south side is exposed, and the west side is exposed, as well as the top side is exposed. The bottom side is not exposed. So this is how we can classify it. Or we could say that this one right here, so I'm I guess making up for the offset, so the one I'm actually pointing to, it could be considered a nub top because we're considering a nub. If we go to our faces here, we select the layer nubs roof, so select objects. You can see a nub is a shape that has 1, 2, 3 sides exposed. Its fourth face here is an interior face, and then it has its top exposed. So if we look back at this pile of voxels, this one right here fits the bill, right? It has 1, 2, 3 faces exposed, its top is exposed, it has one interior face, and its bottom is interior. So those are the classifications. So if we look at Grasshopper, what we're doing is we're taking all of these side faces, so all the tops, the bottoms, the northeast, southwests, we're putting them into one big pile. So we're saying every single point in this list of face center points, we want to compare it to every single point in that same list. So essentially what we're doing is, let's say we look at a little 2D diagram. We're doing the same kind of algorithm except for a set of two-dimensional rectangles. We have these points, which are the center faces. We want to classify these squares into, shapes that either share faces or don't. And what we'd say is for each of these points, test if they share a space or get extremely close to another point in the list. So this top points component here that's grafted represents the point we want to compare to, and these flattened points here represent the entirety of the point. So what's happening is this point here compares to that point, 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 compares to that point. So that point compares to all of those points. And because it does not occupy the same space or is not extremely close to any of this big group of points, we can say that this face is exposed. Versus this point in the center here, which I've already kind of, drawn over. But this point right there, oh, that's so weird, is in the same spot as this point right here. So that's the algorithm that's going on right here. So you can see what's happening is these points are comparing to all points. If you look at this closest points component, it's going to have the distance coming out. We're selecting the second item because if you think about it, since each point is comparing to all points, the first point it's going to compare to is itself. Therefore, it'll have a distance of 0. So that's why we find the two closest. So the count here you can see is 2. We select the second closest one. And then we say, is it smaller than or equal to an extremely small number? So in this case, 0.0001. And the reason why we do that rather than just saying, is it equal to 0, is because sometimes there's a difference between the tolerances in Rhino units versus Grasshopper units. Once we get that, we essentially invert the Boolean. And the reason why we invert the Boolean, that's this little black/white logo there, is right now we're testing then, is it smaller than or equal to a very small number, aka is this face not exposed? But what we want to do is we want to essentially delete all the faces that are covered or not exposed. So that's why we invert the Boolean, because we want to get a false whenever the face is not exposed. So the final step here is out of this Boolean, we get a true, 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 true. So we get a true whenever the face is exposed. So for example, in Rhino, these, all of these faces in this floating piece are exposed. So that's why we get a whole bunch of trues when we were looking at this one. But for instance, on this piece right here, making up for the offset, so the arrow's in the right place, this place here has 1, 2, 3 faces exposed, plus a top exposed. So if we are going to look at this list, it would be something like true, 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 false, true, false. We trim the tree at the end of this to sort of group these trues and falses into the 6 sides of each voxel. So that's where we left off. I know that's like a really quick recap, and it's also probably the most complicated algorithm for some of you that you've encountered in Grasshopper, but it's just kind of this like way of translating geometry into logic and working with Booleans that makes Grasshopper so powerful. So before we start thinking about how we're going to classify these, does anyone have any questions about that quick review? Okay, great. So with that being said, we're going to move forward. So now, I don't know about you, but I cannot keep in my brain a bunch of trues and falses and say true, 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 false, true. Oh, that is a, I guess it would be a column with a roof. Like, that's that classification. It's kind of hard to see, right? So instead, what we're going to do is we're going to convert these trues and falses to norths, easts, souths, wests, tops, and bottoms, so that we're able to, in the Grasshopper canvas, kind of get a sense of what the piece actually is. And from there, this will allow us to build up kind of more intuitive, logical tests later on. So I'm just going to look at my notes just to make sure I'm doing this right. And yes, I am. So what we're going to do is we're going to essentially just make a list. So because we know, if we go back to our faces list right here, you can see that we have the north, east, south, west face, and then top and bottom. What we're going to do is we're just going to make a list. So I want you to go to parameters, input panel. I'm going to turn on caps locks just because, you know, north, south, east, west. The usual standard is they're capitalized, so we'll just keep everything capitalized. So I want you to type N and then enter to start a new line. E as in east. S is in south. W is in west. T is in top. B is in bottom. So north, east, south, west, top, bottom. So these are going to be our classifications. Click OK. With a panel, if you want to have more than one row of data, if you want this to be formatted the way that a list is formatted in Grasshopper, we can just right-click the panel and go multi-line data. So again, that's right-click the panel, go multi-line data. And now you can see our northeast, southwest, top, bottom is in a single list with a path of 0. So again, a path is an address of a certain branch, and indices, or, you know, local numbers 0 to 5. So that's great. Now simply what we're going to do is we are going to use the output of this trim tree component to call this list here. And what that's going to do is it's going to call the sides that are not exposed for each voxel. So let's go to set, let's go to sequence, and then call pattern. So that was set, sequence, call pattern. And essentially what we're going to do is we're going to take our panel here that has the northeast, southwest, top, bottom. We're going to plug into list. And then we're going to take our trim tree output and plug into the call pattern. I'll just delete those two panels that are kind of floating there that I was using just to talk about what we were doing. And I'll put another panel coming out of this call pattern to see what we have. So the fast way to create a panel is just to double click on your canvas and then type panel. So just double click on your canvas, type panel, and plug the call pattern into that panel. So you can see what's coming out here is now a northeast, southwest, bottom. So if we think about that, that means that voxel number 1, at least in my case, has its north face exposed, its east face exposed, south face, west face, and bottom face is exposed. So let's go see what that means. If we go back to our, and you don't have to follow along with this, I'm just kind of showing it on mine. So the bounding box, if I just go to set list item, and I'm just grabbing the first one, you can see that my first item here is actually not a column roof like I was saying, it's actually the column bottom. So it's exposed on all 4 side faces. Its roof is an interior face, and its bottom is, you know, technically exposed, but this means it's just at the bottom. If I click on this to look at the second item here, so this to me it looks like, let's see what it is and see if it makes sense. So this one has its east face exposed, so east, there it is. Its south face exposed, there it is. Its west face exposed, yep, there it is. And its bottom face exposed. So you can see that this algorithm works properly. It's sort of giving us, you know, the coordinates, the exposed faces for each voxel in this entire pile. And we can use this sort of list of letters to kind of start to classify them, right? So, Gabriella, my trim tree has a warning bubble saying that the collapse depth is too large for 6 branches. They were omitted. And if that happens, I can double check on your file. But I think what that might mean is just that you need to re-reference your voxels. So essentially select all the voxels that you want to reference. So for example, just select this pile of voxels here. I did that by right-clicking this layer, going select objects, and then right-click voxel, it puts and go set multiple meshes. So that could be something that's causing that. Essentially what that means is just you probably have some empty layers. And if that doesn't fix it, just let me know during break and I'll take a look. Okay, so once we've done this, maybe what we can do now is we can just group these components here. And I'll right-click this group and I will call it converting trues/falses to list of exposed faces, like so. So I'm just referring to my notes. Yes, so this is the fun part. So let's go and take a look at our different classifications we want to do. So if you're working with this version of the site file, so the most recent one, you're going to have this pieces layer, right? And under the pieces, you're going to have all the classifications I've come up with. And like I said, they're ordered from this list, right? So all the layers here from top to bottom, they correspond to the left to right. So for instance, if you right-click the interior roof layer and go select objects, it's going to select the object on the furthest left right there. Now let's try to classify all the interior roofs in our piles of voxels. So I'm just going to go and see what we're talking about here. So you can see this is my interior roof, right? And what I'm considering an interior roof is that only the roof is exposed. So you can see that I don't have any walls on all 4 faces. I'm going to consider this bottom sort of like a shared ceiling of a different layer. So essentially I'm saying only a roof is exposed. So the question is then, how can I test for that in Grasshopper? So how can I look for this condition in this pile of voxels based on my lists of northeast, southwest, top, bottom, etc., etc.? So does anyone want to turn on their mic and take a guess? So if you were, don't tell me through Grasshopper components. Rather, just tell me in words, what could you kind of suggest to me to test for voxels that only had their roof exposed?
Could it be like a if-then statement? Like if these 3 faces are exposed, select this following room configuration?
Yes, who was that?
Ranveer?
Ranveer? Yeah, so
Yeah.
that's exactly right. So essentially, what Ranveer was saying is we're going to be using something just called, you could call it logic, but in this case, it's Boolean logic. So essentially, we're going to set up a bunch of tests. So in particular, we could think of trying to find this voxel that only has the roof exposed as if a voxel list has, let's say, one face exposed and that face happens to be the top, then it is a roof, or it is an interior roof voxel. So we can sort of classify it that way. So, and that's what we're going to do for all of these. We're going to set up statements saying if a certain voxel meets these conditions, then it is something. So that's what we're going to do. In particular, for the roof, for this first example, it's kind of a more basic one. We can think of a few things to sort of suss out if it's a roof voxel. We can say, does it have the top exposed? AKA, does it have a T in its list? As well, we can also say, well, if it's an interior roof, it's only going to have one face exposed. So we can also say, is the top face exposed? And then also, is there only one item in the list? So you can see in my list, number 367, for example, is probably a roof piece because only its top is exposed. So that's what we're going to do. So let's sort of do that for the roof. So the way we can do this is we can test for the letter. So what we want to do is we want to, here, and actually this is something, there we go. So if you don't know how to do this, in your own notes, if you're ever like, where is that component again, because it's not something you use very often, you can always go Control-Alt, click something, and then it's going to show you where it's located. I just wanted to make sure that it was match text and not a match set, because I've made that mix up before. So what we're going to do to test and see if there's a T in this list, we're going to go to set text and then match text. So set text, match text. The text that we're going to match, actually what we're going to do is we're going to try to set this up so it's kind of easier to do in the future. So just so we can copy this group. We're going to go to parameters, primitive text. So parameters, primitive text. We're going to right click this text and we'll go call this input text here, maybe input text here, because we're gonna keep on copying these tests over and over because we can reuse big chunks of them, right? So the input text here will plug into the text. So text to match, for example, let's plug in our call pattern output. So I'll take this panel, plug in input text here. So our call pattern is going out into our input text here, which is going into our match text. And for the roof, we want to make sure that it has a T in the list, right? So it has an exposed roof. Yeah, Megan.
Sorry, what was the input text?
Oh, the input text was a primitive text component.
Oh, text. Okay, thank you.
Yep. So the pattern that we want to match is going to be T. So what we can do is we can go to parameters input panel. We can put that on the canvas, or else you could just double click and type panel. I'll right click this panel and I'll just call it, I'll label it letter to find. Just to remind ourselves that's what this panel is going to do, and I'll plug that into pattern. In this case, it's going to be T. We're not going to worry about the regex pattern for matching. And then the case, compare using case-sensitive matching. It's good to be, accurate, and if you're trying to match uppercase letters, in this case, you should, use uppercase, but just to save any kind of future bugs, just in case we forget to capitalize something, we'll right click case, and go to set boolean equals false. So that's what we're going to do. Now, if you look at what's coming out of here, you'll see that we have a whole bunch of false, 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 and then, you know, wherever there's a T, there's going to be a true, right? So there's a true. Here's all these falses. So since we're just testing for the kind of presence of all of these, what we can do is we can just add up all these falses and all the trues, and then just to test kind of overall. So what I mean is we can go to maths, operators, mass addition, plug in the match output into the mass addition input, and then what you'll see is a bunch of zeros and ones. And the reason why you see a bunch of zeros and ones is, remember that trues and falses can instantly be converted to zeros and ones, where 1 is true and 0 is false. So for example, in this first list right here, we have false, 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 false. So when we're doing a mass addition, what we're asking Grasshopper to do is to add a 0, a 0, a 0, a 0, a 0, right? So then the answer is going to be 0, which we can convert back to a false. False. There are no top exposed faces in this voxel. Whereas if we go down in this list, for example, this list here, it has a false and a true. If we convert it back to a Boolean after adding it up, it's going to be a true, because 0 plus 1 equals 1, 1 equals true. So that's the logic here. We're using the mass addition to test if there is the presence of a true or a false in here. So like I said, our results are zeros and ones because we used mass addition. But to convert them back, what we can do is we can go to primitive Boolean. So primitive Boolean. We can take our result and plug into the Boolean. And now this Boolean, we can plug it back into this list. And now you can see we have a bunch of falses and trues. So wherever it says false, it means there is no exposed top face. And wherever there is, it says true, it means yes, there is an exposed top face. Now, we can kind of use this Boolean in another way, and you'll find that in some of the classifications, you might want to test for the presence of something, so the presence of an exposed top face, but you might also want to test for the absence of something. So for example, you might want to test for, are these faces, so 3 side faces exposed, a top face exposed, but, so these 3 faces are exposed, a top face is exposed, but there is an absence of an exposed bottom face right here. So to test for an absence of something, what you can simply do is you could right-click this Boolean, go invert, and now instead of saying, for the first item false, there is no exposed top faces. Now what we're saying is true, there is an absence of exposed top faces. Now this might seem like it's getting a little bit in the weeds, but as you go through and try to classify different faces, what you might find is that you need to test for the absence of something to differentiate, let's say, a corner piece from a column piece. So to remember this, what we're going to do right now is we're just going to take this Boolean. I'm going to right-click outside of it, just this one little component here. I'm going to right-click the group. So, sorry if I didn't say it. Select the Boolean component, right-click outside of it, go group. You can right-click the group and change it to blob outline if you want to. I like doing that when I'm trying to remember something about a specific component or writing a note to myself. And then I'll right-click that group, and I'll say invert Boolean to test for an absence, right? So again, what that means is you just right-click a Boolean, go invert, and that will test for an absence of a value rather than the presence of a value. So what we have here, and I can just leave this panel at the end, is let's group these. So from your input text, actually let's group it from the letter to find all the way to the end there. Let's group that, and we'll right click this group and we'll label it testing for a letter. So that's what that looks like. One other thing we can do that might be useful, I like doing this whenever I have something, you know, that I'm gonna have to duplicate this a lot, is this panel right here that I have, the letter to find, I can right click it. Let's go to font settings and go to custom font. And let's just increase the size, you know, to something like 24. Just make it big, you know, make it a different text if you really want. I'll go Gothic. Actually, no, I won't. I will go to this, sure. And essentially this is just, you know, a larger T that sort of lets me know we're looking for a T. So this is how we test for the presence of a letter or test for an absence of a letter in one of these voxel lists. So does anyone have any questions about that? Okay, so since we're testing for a T, essentially what we can do is now we can just start calling these lists. And I want to show you why we need to test for more than just a certain letter. So you don't have to follow along with this, but I just want to demonstrate this to you. So maybe just sit back, don't follow along with this. So we have all these trues and falses. What we can do is I'll just go to set sequence call pattern, these booleans being my call pattern, and the bounding boxes being the list I'm going to call. I will graph that, and essentially you can see what we have here is all of the voxels where the top face is exposed. And that's great, but if you think about it, what we're really looking for is all the voxels that only have the top face exposed. So in other words, we need to create another condition, because if we look at this list, you can see that, for example, this, what I call a nub, it does have the top face exposed, that's why it's giving us a true, but it also has all these side faces exposed, as well as the bottom face exposed. So it's not a top piece, or it's not the interior top piece that we're looking for. So we need to create another little piece of logic to test for the top interior faces. So can anyone think about what piece of logic we could use that's simple, that does not use letters, but rather counts things, that would be able to separate the top interior faces from, let's say, all the other kind of voxels that have their top face exposed? Yeah, Cicely, you're absolutely right. List length equals 1. That's perfect. So that's what we're going to do. So what Cicely's suggesting is that we look at the length of all these lists. So for example, you know, this first list has northeast, southwest, bottom. Let's look at one that has a T. So for example, this one here has the east face, the south face, and the top face exposed. You know, we know that's not an interior top, but the way we can test it is T in this list, which we test here, and does the list equal 1? So is there only one face exposed? So what we can simply do is we can go to sets, list length. So that's set list length. The input text here component, we can plug into the list length. And now you can see, I'll just grab a panel so we can see it. We have all these list lengths, right? So 5, 4, 3, 2, 1, what we're looking for. So what we can do is now we can test for a length. So we can go to math, operators, equality. So that's math operators equality. Let's plug the list length into the first number. The second number, let's grab a panel. Maybe I'll just copy this panel here because it already has the big font set up. So I'll just go Control-C, Control-V with that panel. If you're unable to use that on your computer, the shortcuts aren't working, you can also go Edit, Copy, Edit, Paste. This panel, I'll right-click and I'll change it from letter to find to list length to compare against, maybe. And now what I want to enter is 1. So list length to compare against 1. And I'll plug 1 into there. And now what you're going to see we get is a bunch of trues and falses. So let's go parameters, input panel, plugs this, I'll plug this panel in here. And now you can see I have a bunch of, falses, and eventually I'll find some trues in there. So true, great. So if we think of this though, if we were to test all these voxels for a list length equals 1, that would be great, but it also wouldn't give us everything we need. Because if you think about it, for example, this side voxel right there, which is a side face, it also has a list length of 1. It's just that its one exposed face is a north and east to south or a west, right? But these two conditions together, so does t equal true, does 1 equal true, together those give us the interior roof voxels. So what we're going to do is we're just going to group these components we sort of made right there. So let's just group them. We'll right click this group and we'll call it testing for a list length, like so. Perfect. Now what we're going to do is we're going to use an AND condition. So simply what an AND condition means is it's just, we use in, daily speech every day. We say, is something and something the case. So in this case, is t true, is 1 true. So what we can do is we can go to math, operators, gate AND. So again, that's math operators, gate AND. And we can plug in our letter test, our list length test, and now this is going to give us a bunch of trues and falses that come out. So we'll be able to see, some trues and falses that come out this way. Now, what we'll do in this case is simply we will call our list of voxels. So we will go to set, sequence, call pattern. We will take our AND result, plug into the call pattern, and then our list is going to be our voxels. So that's if we go all the way back to our beginning of our definition, we can just put in our voxels. Actually, why don't we put in our bounding boxes? That's what we're going to do. So we're going to take our bounding boxes, we're going to put into that call list. But first, before we do that, why don't we just create a little component in between them that we'll graft, and then we'll also use it to clean up our definition. So let's go to parameters, geometry, box. Take our bounding box, plug into box. We can just right click that box component and we'll call it bounding box. Oops, caps locks is still on. We'll call it bounding box from box is from voxels. We'll drag this component to the front. And and we will essentially, so we can do two things here. Maybe what we'll do is we'll flatten the call pattern. So you can see this is grafted, hence the dashed line. We want to make sure that all these results are one list. So why don't we just right click, let's go right click the call pattern, go flatten. So now if we hover over the call pattern input, you can see 972 values in one list. And then we can take the bounding boxes from voxels, plug them into the call pattern. We can preview off the bounding boxes from voxels. And if we select the call pattern, you can see what happens is that it is only selecting the voxels that are of the interior face condition. So does that make sense to you guys? Okay, so I'm going to take that silence as a yes, it makes sense. But we're going to do another example just to kind of test it out. So let me see. I'm going to look at my other lists of stuffs and see something else. I'm going to choose a very complicated one. So I'd say that's the easiest one. Now what I'm going to do is choose the most complicated one. And then after that, I think that you guys will have the tools to sort of work through everything. RS. Yes.
Hey Thomas, just quick question on voxel size. So what if our voxel sizes are different than yours and we're trying to input these same geometries in it? Would it stretch out the units to fit into the voxel, or would it just kind of place it in?
What units are you? So are you referring to the
pieces?
So are you talking about the list length, or?
No, I was talking about the geometries that you drew in the pieces. So interior roof, interior bot.
Oh, okay. So you're wondering. Okay, yeah. So that we will address that in a later class. So the question, as I understand it, was, will we be able to essentially create geometry that falls outside of a given voxel, or if someone has a different size of voxels, will we come up with geometry that's flexible enough to populate any size of voxel? And the answer is yes. We won't get to it this class, but that will be starting to look into it next class in the beginning of the following week. By that point, everyone will have the tools to populate whatever size of voxel they want. So yeah, if yours is different right now, don't worry about it.
Okay, cool.
No problem. So I think this is the corner roof. Yeah, so we're going to look at the corner roof to sort of look at a more complex version of how you could classify something. Now, what I'd do is when you're working through it, you can see in this voxel classification, this file I have here, essentially, it looks like there's a lot of crazy stuff going on, right? Like, whoa, that's a lot of grasshopper. But really, what's happening is I'm just classifying these different classifications based on the different layers I have here, right? So, for example, I have interior roof. That's how you select interior roof. I have interior. That's how you select interior. And then moving on, for instance, I have tunnel roof. You can see tunnel roof. I have tunnel, tunnel, tunnel bottom, tunnel bot, tunnel floater, tunnel floater. So for instance, that's why, this is a file that has all these different conditions sussed out. But for the most part, you'll see it's just the same thing copied and pasted and copied and pasted. And usually I say it's kind of bad grasshoppering to like copy and paste stuff. But for a situation like this, it actually just makes a lot of sense. If you're not going to script this in C# or Python or something, your definition's just going to look like this, just so it logically makes sense to you. So that being said, what I would do when you're starting to classify these by yourself or as a group, once you're done one classification, like we were right here. So for example, we have our, top interior voxels. maybe just go to Utilities, Scribble. So Utilities, Scribble, drop it on the canvas, type the classification here. So in this case, it is interior roof. Maybe change the size to something that you can see from a distance, because it will be a big definition, like 48. Maybe even bigger than 48. Let's crank to 100. Interior roof, like so. And then just group this set. So here's your interior roofs, right? So what we'll do is we will try doing a corner, let's try doing a corner floater. So what I'm going to do to start doing a corner floater, so first of all, let's review what a corner floater is. A corner floater in my sort of classification system is something like this, and I am making up for the arrow offset. So you can see I have 1, 2 corner faces exposed, and then I have a top face exposed and a bottom face exposed. So that's kind of what I consider a corner floater. Again, if you're not sure what a certain classification is, you can always go to the layer, go select objects by a layer, and it's going to kind of show you what I mean. So you can see this is a corner piece, and the top's exposed, the bottom's exposed. Also, just ask me if you're not sure what something means. So let's do corner floater. To start off, just take the work you've done already. So I've selected everything that's in the interior roof. Go Control-C, Control-V. I'm going to ungroup the big group like so. So ungroup. And then I'm just going to start by changing this. So instead of interior roof, I'm just going to rename it corner floater. Like so, just so I know what I'm working with. And now I can just start thinking about the logic of a corner floater. So a corner floater, give me an idea. And then also what I'm going to do is maybe what I'll do is I'll take this call pattern, the bounding box from voxels, and I'll disconnect this call pattern, because I know that I'm going to have to do some more things. So what we're left with is just one testing for a letter and one testing for a list length. And corner floater, I'm going to say, is probably the most complicated of all these classifications. So, but does anyone want to take a guess, or, you know, just explain to me in sort of everyday language what you would test for if you were looking for this corner floater piece?
I'll test for both the exposure of the top and the bottom faces.
Yep.
So that's the first requirement.
Yep.
And then I'll mix the conditions, something like 2 out of the 4 out of faces are exposed as well.
Yeah, that's perfect. So we can add up those kind of comments. So the first thing let's do is let's test if the top and bottom are present. So we're already testing if the top is present, right? So this test right here, we have our testing for a letter group. It's already true for T, for, you know, the spaces it needs to be. What we can do is we can just select this group, go Control-C, Control-V, and we can change the letter to find to be B. So B. So now we're testing for the top and the bottom, and we can plug this true or false coming out of the bottom into our gate and, right? So now what we're doing is we're testing for a top and a bottom. Those are the first 2 conditions we're setting up. I'm just going to move our testing for a list length down. Now, this is why this one's a little bit complicated. So whoever just spoke, sorry I couldn't see your name, but you were right in that you kind of sussed out that we need to test for 2 faces in particular. So it's not any 2 faces, because if you think about it, what I'm calling a tunnel, let's find a tunnel. what I'm kind of calling a tunnel, for instance, or let's say a nub right here, it will have these two faces exposed, right? But they're opposite faces. What a corner face, or what a corner voxel has, is two faces which are next to each other exposed. So for example, it will either have the north and the east face exposed, the east and the south face exposed, the south face and the west face exposed, or the north face and the west face exposed, in any of those combinations. And that's why the corner piece, I'm going to say, is the most complicated of all of them. Just because it's a lot of things we need to test for to make sure it's not something else. So let's start doing that. We can just select both this top group and this bottom group. So I've just selected all these components here. I'm going to go Control C, Control V. And let's think. So if you think about this is, let's say, where my mouse is now, making up for the horrible offset, so I am aware of the offset. So let's say this is north. You can imagine that if this were a rotated corner face, it would say that north and so north and east face are exposed. So those two in that specific combination are exposed. So what we can do is we can go letter to find equals N, letter to find equals E, so a northeast corner, and we need both of these things to be right, or to be true at the same time, right? So let's go to set, or let's go to math, operators, and plug in the two outputs. So the true for the north, the true for the east. Yes, RS.
Could we plug in the E by holding shift into the same one as we plugged in N? Does that make sense? We have two panels going into...
yeah, no. Maybe. So the question here is, can we do this? Like essentially hold shift, and
right.
I'm not sure. Actually, maybe. Let's see. Here, let's test this out. No, we can't do that because it's still going to give you a positive because it's matching 1. So it'll give you false positives. So the question there was just, can we kind of double up, and instead of having one, instead of having one group of definitions for each letter, can we just double up on the input? But it looks like we can't do that because it'll give you false positives. If there's one is true, then it's going to give you a true even if the other one is false. So, I mean, it's a nice thought, but unfortunately in this case we can't do that. So we'll just stick to this way. So the north and east, that's the first set of, the first group that we want to test for. What we're going to do is we're going to copy these two components as well as the and out. So is north true, is east true? Both going into an and. Let's go Control C, Control V. Now if we think about this, the next corner, if this is north, this is east, the next corner is going to be one that's east and south, right? So east right there, south right there. So instead of north and east right here, I'm going to put in east. So E is in east, south, so S is in south. So I have my north, east, east, south. Just going to keep on moving down that number one, the number test. Now I'm going to copy the east and south because we still need to test again. Now the next corner piece that we could have is one that's exposed on the south face and the west face. So let's put in an S for south, W for west, And then finally, let's copy the south and the west, Control C, Control V, to give us the final one, which is the north exposed and the west exposed. So a northwest corner, that's the final one. So north will be my first test, west can be my second test. So what we're testing here is northeast exposed, is east-west, or east-south exposed, is southwest exposed, is northwest exposed. Can anyone tell me, and we're testing that both of these things are true at the same time, can anyone tell me what Boolean operator we want to plug all of these tests into? So out of and, not, or XOR. So what we're going to do is we're going to plug into gate OR. Perfect. RS, gate OR. So math operators, gate OR. So the reason why we're plugging into gate OR is what we're testing is north and east true, or is corner east south true, or is corner southwest true, or is corner northwest true. So not are they all true at the same time, but is one of these four true. So what we can do is we can take our gate and output, plug into gate OR, take our second gate and output, plug into gate OR, take our third gate and output, plug into gate OR, and what we have to do now is zoom in and click the little addition icon on gate OR, and then we'll plug our result into C, and then finally our last test, which is the northwest corner, we'll plug into D. So all those together are saying if any of these corner conditions are true, it's going to give us a true. So now our two kind of main tests here are, is the top exposed, is the bottom exposed, and is one of these conditions satisfied, one of these corner conditions satisfied. So we can take our gate OR and plug into our upper gate AND. So this gate AND that has the top and bottom test going into it, we can just zoom in, click the little addition icon to get the C input, and then take the gate OR output and plug it into C. Yeah, Natalie.
I just want to ask, so what happens if we, like, at the gate OR, we have like multiple conditions which are true at the same time? Would it give like a false, or would it give also a true as well? Because we don't want, all the faces to be exposed.
Well, exactly. So Natalie, you bring up a really, really good point. So stay on the line and we'll sort of talk this through. So you're right. If let's look at this condition here. Okay. So there's my mouse making up for the offset. So in this case, Natalie's absolutely right. You can look at this and you can see that the north face is exposed and the east face is exposed. So this corner will give us a true. But this corner will also give us a true. This one will give us a true. This one will give us a true. So we'll have four trues coming out of our ANDs, which will give us a true result. So far, the top's exposed, the bottom's exposed. We get trues coming out of all the sides. So if we were to leave our test as it is right now, you're right, we would get a false positive for this free floating voxel. So the question is, what kind of list length test can we use in conjunction with these side tests that would take this top floating piece out of the out of contention for a corner floater piece? So if we go and look at the corner floater piece right here, how many faces are exposed? 1, 2, 3, 4. So what we can do now is we can go down to our testing for a list length, and we can just change this 1 that we copied over, change it to a 4. So now it needs to satisfy all of these as well as have 4 faces. So when we zoom into our gate AND at the end, so this is the gate AND that are testing for T, testing for D, or B, testing for all of these kind of corner conditions. If we zoom into it, click the little addition icon again, so we get A, B, C, D input, and take this testing for a list length, list equals 4, take the equality and plug it into gate D. Now we should have a fairly robust test that's only going to give us the corner conditions. So what we can do is we can take this result and plug into our call pattern, and now you can see that what we get are our corner floaters popping up. So that was a great point. It's how do you further refine this? And this corner floater piece right here, what I'd do is once I get to that point, I'd just group it. And I'd say, okay, this is a corner floater. And what I'd do when I'm working through all of these, I would, just build off of what I have. So for instance, a corner top, so a corner roof. So let's say a piece like this, for instance, right here, making up for the arrow offset. I could just simply copy my corner floater algorithm and then change a few things. So first what I'd do is I'd change the name from corner floater to corner top. And then simply, I know that all these corner conditions are still true, right? But what I could do is I could say, instead of letter to find top, or letter to find T equals true, I'd leave that, but letter to find B, I'd set it to false. So to set this for false, what I could do is I could just invert Boolean to test for an absence. I could right click the Boolean, go invert. And then if I look at my corner top condition right there, I can now see that I have 1, 2, 3 faces exposed instead of 4. So what I'd do is I'd go down to my list length, change that list length to 3, and then just double check visually that I have selected the correct pieces, and it looks like that test worked. So does that kind of make sense? So with that kind of reasoning, I think you actually have enough to really find all of these conditions. So what I'm going to do is we're going to take a break, unless there's any questions. So any questions right now before we take a break? Yeah, Jeremy.
Yeah. Can I just get you to look at my script, I guess, during the break?
Yeah, of course. Yeah, I'll stick around during the break. But what we're going to do after the break is at 7, maybe 7:35. So we'll take a 15-minute break. And please stay logged in, because what I'm going to do is I'm going to try to group us into breakout groups. So I'm hoping that I can get this right. Like you're learning Grasshopper, I'm learning Collaborate Ultra. So hopefully I can get it done. But the idea is that we're going to break out into smaller groups where you can converse with your classmates. So, please turn on your mic. I believe you'll be able to screen share as well with your classmates. But the idea is within your groups, again, that are on this sheet right here, you will be able to kind of figure out the rest of these classifications. And what I'm going to do is I'm going to sort of check in with your groups for the duration of the class, and you can ask me a question. So hopefully it kind of simulates the in-class breakout group work session portion. So I'll try to figure this out during the break, but I will see all of you back here at 7:35. Thanks.